Hello, everyone. I think you just found your U, and we're going to keep working with that. So U substitution, but on definite intervals. So what's that again? What's that language saying? So recall from the last video what U substitution was. So we might have an integral, and we have looked at this example with you, cosine of x squared times 2x dx. Well, what last video was on is since U substitution is we're going to find the part in the integral where the derivative is within there, because then when we take the derivative, we account for that. So U here is going to be x squared, where if we differentiate both sides with respect to x, you get du dx is equal to 2x, and then multiplying the dx to the other side, you get du equals 2x dx. And these two lines, the u equals x squared and the du equals 2x dx, helps us rewrite this integral as cosine of u, and then the 2x dx, we can just write du. Okay. And now we have a different function, just in terms of another variable, that we can integrate a lot easier, because the integral of cosine is just sine of u plus c. And then we just replace u when we're done, and that was our answer. Okay. Now, how does that relate to a definite integral? So a definite integral is it's the same idea, but instead of it being an open bound, we're just looking for an antiderivative function. Now we're looking for the area under the curve. Definite integral just means definite just means you can think about it as like a closed interval in a way. So what if we were going from 0 to pi halves of cosine of x squared 2x dx? So now this, if we applied the same U substitution, is we already know, if I work through this, is that this is going to equal sine of x squared as the antiderivative from above, and then we'd evaluate it from 0 to pi halves. Well, if I do the work really quick, it's going to be sine of pi halves squared. So that would be, let's do pi halves, well, do pi squared over 4, minus the sine of 0, which is going to give me the sine of pi squared over 4, which I don't know what that is. We'll put in a calculator really quick. Let's look. Sine squared of the sine of pi squared over 4. And what we get here is approximately 0.624. Okay? We'll keep this in the back of our head. Now we did that by rewriting the function x, but could we have done this earlier, right? So my question to you is, if you use U substitution, if we let u equal dx squared and we let du be 2x dx, could we do cosine of u du from 0 to pi halves? Can we do this? Right? Well, let's look. If we just stuck with u, then that would be sine of u, and then we'd be evaluating from 0 to pi halves. Which, if you plug that in, you get sine of pi halves minus sine of 0, which is going to give us 1 minus 0, which is 1. And wait a second, that's not the same as what we got. So you can see that U substitution with definite integrals just have to be careful of bounds, because the bound 0 to pi halves were in relation to the function with x. So this worked when we put the function back in terms of x. If we try using those same bounds, but with u, it doesn't work out, right? These bounds have to be in terms of x. So one approach is you could replace the u with x and keep the same bounds. But there is another approach you can do to solve these problems. And the second approach, which I'll show you right here, is that you find your new bounds for your function in terms of u. That's in terms of u. So what do I mean by that? So the integral of cosine of u du is sine of u. Right? Now we don't want to go from 0. Let me put sine of u. Now we don't want to go from 0 to pi halves because those were the bounds for our function in terms of x. What are they in terms of u? So we would have to plug this into this function x squared to figure out what those bounds are. So then that's going to give us, so side note, if u equals x squared, well, we have to figure out what is this when it's pi over 2 squared, what's that new upper bound in terms of u, and then 0, what's going to be the bound with 0? So 0 is going to stay the same. If you plug 0 into u, it's still going to be 0. If you plug pi halves into u, we're going to get pi squared over 4. And now when we do the integral of this, notice that we get sine of pi squared over 4 minus sine of 0, which note, this now is what I had up here, which is what worked when you replaced it with x. Okay, and notice that that would just give me sine of pi squared over 4, because the sine of 0 would go to 0, and that is going to be my same answer that I got up above. So those are the two techniques, and we'll look at one or two more so you can see this. Is you can either replace u with x and keep the same bounds, or find new bounds for your function in terms of x, or in terms of u, sorry. Okay. So let's look at one more, let's look at maybe two more examples. Okay, let's do the next one I had on my paper. The integral of 3x squared times e to the x to the third dx. And we're going to evaluate this from 1 to 2. Okay, so the 1 to 2 makes it closed. So let's do this both approaches. The 1 where you replace u and keep the same bounds, or 2, find new bounds in terms of u. Right? So approach 1. So that is, we're going to remember to replace u with x. Okay. So if we let u equal x to the third, then du would give us the 3x squared dx. So I can rewrite this integral as u e to the u du. And then we're going to replace u with x. Well, that's after the antiderivative. So the antiderivative of e to the u du is just e to the u. And then we're going to replace u with x. So then we'll make this e to the x to the third again. And then we're going to evaluate it from 1 to 2. Okay. And what we get there, if we keep going, is we'll have e to the 2 to the third minus e to the 1 to the third, which will give us e to the 8th minus e, which is e to the 7th. No, you can't combine those. That's wrong. That's your final answer right there, is e to the 8th minus 1. Let me make sure. You can't combine them because of subtraction there, and they're different powers, and I just want to make sure. E to the 8th minus e to the 1st, and is that the same as e to the 7th? Yeah, it was. I didn't think it was, and I just wanted to verify. All right, so there's one approach, and we know what the answer is, which approximately, in case we have to get to that point, e to the 8th minus 1 was approximately 2,978.240. Okay. So again, remember that this, to spiral back in what we've done, that's the area under the curve from 1 to 2. What we found there by doing the integral. All right, now let's do approach 2. Approach 2, which is we're going to use new bounds for the in terms of u, for the function in terms of u. So we don't have to replace x back in. So then what we had is we would have the integral of e to the u du. And what are our new bounds? Well, if we replace, so this new bound was 1. So what's u equals 1 to the third? Well, that's going to give us 1 still. And then up here, we would have had to do u equals 2 to the third, which is going to give us 8. So now we can do the same integral of the function e to the u rather than e to the x to the third. We just have new bounds. So it's almost like it's just a different function we have to consider. E to the u is a different function than e to the x to the third, and thus they're different functions, want the same area, need different bounds there. Notice if we do this, we would have e to the u from 1 to 8. And plugging those in, we would have e to the 8 minus e to the first. And notice how that's the same thing we got. So both methods work. I mean, it's totally up to you. Both methods work, where you either new bounds in terms of u, which is what I did here, or just replace it with x and keep the same bounds. They honestly have their pros and cons depending on the situation. Hope that helps you with this video, and I hope you're getting a little bit better with U substitution from there. Okay? If you have any questions, make sure you reach out. Bye-bye.